Well, welcome everyone to, I believe, our last TCS Plus talk of the semester. And today it's a great pleasure to have Aaron Bernstein from Rutgers University. He's going to talk about really a breakthrough in algorithms and a near linear time algorithm for negative weight single source shortest path. And before we begin, I do want to encourage everyone to keep their cameras on. It's really nice when you give a talk and there can be some visual feedback for Aaron. And please feel free to unmute yourself and ask any questions throughout the talk. But if you don't want, at the end of the talk, we'll have an unrecorded session where we can just discuss open problems or anything from the talk. And lastly, let me say that we're always soliciting suggestions for, let's say, recent results or even not so recent results that you think would be a great TCS Plus talk. Please, in our website, we have a link to give suggestions, and we always take those very seriously. So with that being said, I'll hand the floor over to Aaron, and please take it away.
Okay, thanks so much, Eric, for the introduction. Thanks everyone for coming. So yeah, this is joint work with Daniel Pandanonkai and Christian Wolf-Nielsen. And so I'm going to be talking about a classic problem, single source shortest paths. So you're given a source, directed graph, and you want to find a shortest path tree from the source. So what are the this is a classic problem we teach in undergrad algorithms. And what are the things we teach in undergrad algorithms? Well, if it's an unweighted graph, you can do it in linear time. And if it has non-negative weights, you can do it in something close to linear time using Dijkstra's. But then once the graph has negative weights, the classic algorithm is Bellman-Ford, which is much, much slower. And so then there's a history of, okay, this negative weight case seems to be much harder. How can we do better than Bellman-Ford? So again, this is the problem. And I'm going to assume for simplicity for this talk that the graph has no negative weight cycle, because otherwise shortest distances aren't well defined. So just assume there is no negative weight cycle in the graph. So again, Bellman-Ford is the classic algorithm for this problem. And so let me talk about kind of the history of improvements over this. So there are kind of three phases for this problem. The first phase was in the 50s, this classic Bellman-Ford algorithm. And then after a while, it remained at MN. And then there was a series of improvements using various combinatorial tools like scaling, price functions. And they brought it down to Emmerden. And then it remained open for a very long time. Can we beat Emmerden? And it was sort of unclear how to do that. And Emmerden also stood as a barrier for many other problems like bipartite matching. And then only very recently did people start making improvements on this using like a completely different set of techniques based on continuous optimization and dynamic data structures. And so they began to slowly break through this Emmerden bound. So what we show is, we can kind of finish this line and we really get something that's like a near linear time. And the interesting thing about our result is that it's actually much more similar to these combinatorial improvements. It bypasses the kind of machinery of continuous optimization, and it's just kind of like a familiar kind of combinatorial algorithm. We're able to show that you can actually use these techniques to get near linear time. Okay, I want to talk about another result that kind of came out simultaneously with ours, which is basically there's also this result that is more continuing the line of the continuous optimization work and is solving the much more general problem of min-cost flow. So that running time is slightly slower, but they solve a much more general problem. And so in particular, negative weight shortest paths is a special case of min-cost flow. And so they also get the same running time for negative weight shortest paths. And so I want to pause for a second and talk about kind of the general layout of graph algorithms, which is that it turns out that a lot of like the foundational problems of our field, the problems that we introduce in intro algorithms classes, like bipartite matching or negative weight shortest paths or max flow, these problems actually turn out to be really hard. And until recently, we didn't have efficient algorithms for any of these problems. And so now we do have this efficient algorithm because of this sort of breakthrough for min-cost flow. But I think one thing that it would be interesting to do for future work is basically to see if we can get simpler algorithms for these problems. because a lot of these problems, like something like bipartite matching or negative weight shortest paths, it seems like an elementary problem, like the definition is simple, but the only way we know how to solve the problem currently is to go through min-cost flow and use like extremely intensive machinery for min-cost flow to solve these problems. And so it'd be nice for some of these problems to see if there's a more kind of direct, streamlined, simpler approach we can use. And I think that's especially important for these problems because a lot of graph algorithms is basically about studying variations on these core problems or studying them in different models of computation. And so getting kind of simple, efficient tools for these problems might give us more flexibility to solve these variations. So essentially what I'm showing in this talk is that specifically for the problem of negative weight shortest paths, we can come up with a kind of simpler, more direct solution that's also faster to solve this problem, rather than going through the machinery for min-cost flow. But that's only for this one problem. It's still open whether or not you can do it for these other problems. Okay, so let's then talk about the result. So I'm going to start with some preliminaries. So first off, in general, just some simplifying assumptions. Just think of the graph as having constant degree. Think of there as not being a negative weight cycle. You can assume this without loss of generality. Okay, so the first preliminary I want to talk about is price functions. So this is something that I at least teach in undergrad algorithms. So probably all of you have seen it at some point, but it might have been a while. So I'll just very quickly go through them again. So what are price functions? So the idea is that given any graph, if you define any function on the vertices, any price function, then such a price function also defines the new edge weights, where that new edge weight, which we call the reduced edge weight, is the original edge weight plus the price function of u minus the price function of v. And the reason that this is a useful thing to do is because it turns out that any price function you define, if you then look at these reduced edge weights, the shortest paths in the two graphs are going to be exactly the same. And the proof is straightforward. It's basically that for every edge, the reduced weight is adding the price of u and subtracting the price of v. So you can see that for any xy path, all of the price functions in the middle will cancel. And so you only change the path by 5x minus 5y, but these are the same for any xy path. So every xy path gets shifted by the same amount. So the shortest paths are the same. Okay, so price functions are nice, and we're going to take advantage of the fact that we're just going to keep defining price functions and changing the graph by these price functions. And the point is the shortest path structure never changes from this. So you can define any price function phi, but the whole reason we're doing this is because our end goal is to find a price function such that all of the edges become non-negative. Because if you can find such a price function, then you're done. Then you take this graph g phi and you just run Dijkstra's on g phi, and that gives you shortest paths. So we can see that computing a good price function, by good price function, I'm always going to mean like all the edges become non-negative. Such a price function immediately lets you compute shortest paths. It turns out the opposite is also true. If you have an algorithm to compute shortest paths, you also have an algorithm to compute a price function. And the idea is you just take a dummy source, connect it to weight 0 to every vertex, and you just compute shortest paths from that dummy source, and you set the price of every vertex to be this shortest distance. And you can show by the triangle inequality that this is a good price function. All the edge weights become non-negative. So the details aren't so important here. What's important is just that you can always like if you can compute shortest distances, you can compute a good price function. If you can compute a good price function, you can compute shortest distances, and we're going to constantly be translating between these two. Okay, that's preliminary one. Preliminary two is also from undergrad algorithms. So what are the classic algorithms for this problem? So there's Dijkstra's algorithm that is fast if edge weights are non-negative. Then there's Bellman-Ford, which is pretty slow. But Bellman-Ford has this nice property that it is actually fast if you're promised that every shortest path contains few edges. And actually, you can say something stronger, which is that intuitively, positive edges are easy because Dijkstra can handle them. The only hard edges are the negative edges. And so you can actually show that as long as every shortest path contains at most k negative edges, as many positive edges as you want, but only a small number of negative edges, then you can modify Bellman-Ford to again run quickly. And the algorithm that does this is quite intuitive. You basically like start from your source and you run Dijkstra, and that sort of covers a bunch of positive edges. And now you run a single iteration of Bellman-Ford to get the first negative edge. And so this gives you the shortest path that uses as many positive edges as you want, and then one negative edge. And then you just repeat this. You run Dijkstra again, and then one more iteration of Bellman-Ford. So you just kind of swap these iterations of Dijkstra's and Bellman-Ford k times. Okay, so we have this algorithm that works well as long as all shortest paths have few negative edges. So this is sort of folklore. We are going to use a slightly stronger version that we prove that's basically the same, but we're able to show that actually you don't need every shortest path to have few negative edges. You just need the average shortest path to contain few negative edges. And then again, you can compute it quickly. Okay, so this is somehow the main takeaway of the second preliminary is that we have this black box, which is going to tell us that it's easy to compute shortest paths that contain few negative edges. We're just going to plug this in as a black box. And the basic idea of how we're going to use this is, okay, in the input graph, it might not be the case that shortest paths use few negative edges. But the idea is that we're going to define a price function that has this property. So our final goal is to have a price function where everything is non-negative. But instead of doing that directly, we're going to first solve an intermediate goal where we're going to find a price function such that most of your edges are positive. You might have a few negative edges, but you have this promise that the average shortest path has few negative edges under this intermediate price function. And once you find such a price function, then you can use this BF plus Dijkstra to compute distances in that graph. And once you have distances, that gives you a perfect price function. Because again, if you can compute shortest distances, that immediately translates to a perfect price function. So you can kind of see here that we're constantly going to be bootstrapping, where we compute some price function that allows us to compute better distances, that allows us to compute a better price function, and so on and so forth. Okay. The last preliminary is by far the most important and the most complicated, and also a lot of it is kind of new to this paper. And so for this, I'm going to have a whole discussion of low diameter decomposition. So I want to start by talking about low diameter decomposition in undirected graphs, which has been around for a long time, just as a warm-up to give you an intuition for what's happening. So the basic idea is that a lot of problems are easier to solve if the graph has small diameter. Now, the input graph might not have small diameter. And so the idea of low diameter decomposition is to basically partition the graph into vertex sets such that each vertex set has small diameter. So we're partitioning into green clusters, each of which has small diameter. Now, of course, inevitably, you're also going to have some edges between the clusters. And those are going to be harder to handle because they're not in a small diameter component. And so your goal is to basically minimize the number of these red edges. So informally, the goal of low diameter decomposition is to partition a graph into clusters such that each cluster is low diameter and such that there are few intercluster edges. And there are many algorithms that could take advantage of this. Essentially, what they do is they run this decomposition, then they solve the problem inside each green component, which is easy because it has low diameter. And then they also have to handle the red edges, and that's easy because there is only a small number of red edges. So the formal statement looks like this. So for the formal statement, the focus is kind of on the red edges. So our goal is to find a small set of red edges such that when you remove them, the remaining components have small diameter. So we're going to have a parameter D, and the goal is to find a set of red edges, that's ESEP, such that when you remove them, the connected components have diameter at most D, and such that the number of red edges is small. And in fact, we want something even stronger. We want that every edge is a red edge with small probability, something like probability 1/D. Okay, so this is a classic tool from undirected graphs. This has been around since the 80s. It's used in many different applications. But the question is, can we somehow port this tool over to directed graphs? So let's talk about what would the goal be for directed graphs. Well, this is what we had for undirected graphs. And now in directed graphs, we again want clusters of small diameter. But now what does small diameter mean? Well, two vertices should be in the same cluster if they're close in both directions. So we want small diameter in both directions. So ideally, we would have something like this. A bunch of like small diameter clusters, where everyone can reach everyone in both directions, and then a small number of intercluster edges. Unfortunately, this is just not possible. Like this goal just simply cannot be achieved. And the reason is because of DAGs, or dense acyclic graphs, directed acyclic graphs, sorry. So in particular, imagine that you have a DAG. So this has no cycles, And in particular, there are no two vertices that can both reach each other. So there just is no component that you can have that has low diameter. And so because of this, although low diameter decomposition has been used in undirected graphs for a long, long time, it basically hadn't been used for directed graphs until very recently because it just felt like, well, like the natural goal simply does not work. But over the past few years, people have been able to show that actually, no, there is a version of this that you can define for directed graphs that makes sense. And so we're going to be building upon that. And also, like in our paper, we kind of give a more efficient way to compute that decomposition. So let's talk about what this decomposition is. So in directed graphs, you can think of there as being two extreme cases. One extreme case is a low diameter, strongly connected component where everyone can reach everyone. This is a relatively symmetric case in that any two vertices can reach each other in both directions. The other extreme case is the asymmetric case, which is a DAG. A DAG is completely asymmetric, right? For any two vertices, one of them can definitely not reach the other. And in particular, we saw that DAGs cannot be clustered because they're asymmetric. So we have these two extreme cases, which are very different. But the nice thing is that actually both of these extremes are relatively easy, or at least for many problems, we have good algorithms for both extremes. We saw that we have good algorithms for low diameter graphs, but for many problems, we also have a totally different set of good algorithms for DAGs. Intuitively, because DAGs go from left to right, as we see in this picture, you can use dynamic programming on them. And so what we're able to show is that essentially any directed graph can be decomposed into these two extreme cases. And since both extreme cases are easy, that then gives us an algorithmic framework. Okay, so let's sort of define that formally. So again, the underlying goal is we want all of our strongly connected components to have small diameter in both directions. But unlike in the undirected case, we're actually going to have two kinds of intercomponent edges. The first is edges that all move in one direction. So these are kind of DAG-like edges in that they're all moving from left to right, and so they don't create any new cycles. And there's going to be an unbounded number of these. If the original input graph is a DAG, then in fact, all of the edges will be these black edges. So there can be many, many of these, but intuitively, it's okay to have a lot of these black edges because they are DAG edges, and we have good algorithms for handling DAGs. Okay, and finally, the really problematic edges are the edges that go backwards in the ordering. They don't have any nice structure. And so the goal is, like in the undirected case, to have few of these problematic red edges. So here is the formal statement. Again, we're focusing on the red edges. We want to find a small set of red edges such that if you remove those red edges, then all of the strongly connected components in the remaining graph have low diameter. Note that there can still be edges between them, namely the black edges, but the strongly connected components themselves should have low diameter once you remove the red edges. And like in the undirected case, we want there to be few red edges, and in particular, we want that every edge is a red edge with small probability. So it's actually like the definition is quite similar, but you can see it leads to a different graph structure because you have these three kinds of edges now. So this is kind of this idea of direct low diameter composition is something that we kind of started working on in the past few years. And in this paper, we give a more efficient implementation. And another thing to note is that low diameter decomposition only applies to graphs with non-negative weights. That's not going to change. That's still true for our use of it. And so conceptually, it's not really clear why it's going to help in a graph with negative weights. And so one of the things we're going to do is show that even if the graph has negative weights, it can still be useful to apply this decomposition. Okay, so this is the formal statement of the decomposition. And we're just going to apply it as a black box for our algorithm. And let me say at a very high level how we're going to use it. So we have a graph G that has negative edges. So first, we're going to round all the edge weights up to be positive so that we can do low diameter decomposition. So now we run this low diameter decomposition. And we said that this gives us three types of edges: the edges inside the low diameter SCCs, the black DAG edges, and the red problematic edges that can go backwards. And so the idea is we're just going to kind of use different algorithmic techniques for these three kinds of edges. So we're going to have three phases, and each one is going to fix one of these types of edges. So for type 2 edges, we're going to have an algorithm specifically for the DAG edges. And that's going to be easy because DAG edges are easy. So for example, a lot of you probably remember that the negative weight shortest path problem in particular is easy to solve on a DAG. And so that's kind of indication that handling these DAG edges should be easy. Okay, the type 3 edges are going to be easy to handle intuitively because there's only a small number of them. I think the hardest case is actually the type 1 edges. Because I sort of said at the beginning that the motivation for low diameter decomposition is that a lot of problems are easier to solve if your graph has low diameter. And while that's true of a lot of problems, it's not really clear why that would be true of negative weight shortest paths in particular. Because what does low diameter even mean if you have negative edges? And in particular, I kind of said before that negative edges are the hard case, whereas the diameter is more talking about the positive diameter. So it's sort of unclear why low diameter would help us. So that's something that we're going to see in a second, why low diameter decomposition and why small diameter can still help us when we have negative weights. Okay, so those were the three main preliminaries I wanted to cover. And now let me also cover kind of one more standard technique, which is weight scaling. So rather than trying to directly find a good price function that makes everything non-negative, the standard tool used for this problem is to sort of slowly scale so the weights become less and less negative. So in particular, you just want a subroutine that you start with a graph where your most negative weight is like negative 2b, and you want to find a price function that makes the edge weights less negative, so that most negative edge weight is negative b. So this is kind of basically all the previous algorithms of this problem are in some way trying to solve this subroutine. And if you can solve the subroutine, it's well known that you can solve the overall problem. All you do is you start with your arbitrary input graph where the most negative weight might be very negative, and you just repeatedly call this scaling routine. So the edges become less and less and less and less negative until eventually like your most negative edge is barely negative. And you can show that at that point, you can just round these edges up to 0 and it won't influence your shortest path structure because they're already like so barely negative. It doesn't matter if you round them up to 0. Okay, so really the takeaway from the slide is just all we care about is the green part. It's just solving that subroutine to do one scaling step. And in particular, to make this talk easier to understand, I'm going to focus on a specific scaling step, which is for the rest of this talk, imagine you start with a graph where your edge weights, your negative edges are -1 or -2. Those are the only allowable negative edges. And I want to compute a price function such that my only negative edge is -1. Okay, so that's my goal. And here is, so now if we kind of follow down here, here is the plan for this goal, which is we start with this graph G plus 0, which is just the original graph plus a dummy source. So from now on, whenever I talk about a source, I'm always talking about this dummy source that has weight 0 to every edge. The like original input source actually does not matter to us at all. We just care about this dummy source S. So G plus 0 is just the original graph plus a dummy source. G plus 1 is the same graph, but we added +1 to all the edge weights. So our goal is going to be that we're going to find a perfect price function for G plus 1, meaning we're going to find a price function such that in G plus 1, all of the edges become non-negative. And note that in G, that means that your most negative edge weight will be -1, because in G, they're all bigger than 0, and G and G plus 1 just differ by 1. So in the original graph G, they'll be bigger than -1. So essentially, because our goal is scaling, what that means is that instead of having to directly find a price function for G plus 0, which is hard, we only have to find a good price function for G plus 1. Now, of course, the question is why G plus 1? Like all of this, the whole point of all of this is to allow us to work with G plus 1 instead of G. But this raises the question, why is it easier to work with G plus 1? Why should it be easier to find a perfect price function for G plus 1 than to find a perfect price function for G? And this goes back to what I was saying about low diameter decomposition. So here's an informal intuition. Remember that our goal is to compute a price function by computing shortest distances. And we also said that it's easier to compute these shortest distances if paths have few edges, because then Bellman-Ford works well. And so at a very intuitive level, we want our shortest paths to use few edges. And what G+1 is doing is that it's effectively penalizing long paths, right? Because in G+1, you're adding +1 for every edge on the path. So long paths get penalized more than short paths. And so this is basically in G+1, your shortest paths are more likely to contain few edges. More formally, we're able to prove the following, that low diameter decomposition is going to give us these low diameter components. So low diameter on its own is not really useful to us. What we actually want is that shortest paths have few edges. But what we're able to show is that if you have a component that has low diameter in the original graph, then in G+1, all the shortest paths inside the component are actually going to have few edges. So this is why working with G+1 is easier, and we're going to prove this formal claim a few slides from now. Okay, so to kind of just recap, we start with a graph where the most negative edge weight is -2. We want the new graph where it's -1. And we're going to use three kinds of graphs. G+0 is just the original graph with a dummy source. We're basically only going to use that for analysis. The main graph we work with is G+1, which is just the original graph where you added 1 to all the edge weights. And the goal is to find a perfect price function for G+1, where everything becomes non-negative. Finally, we're going to have one more graph, which is G+2, which is just because we want to run low diameter decomposition on this graph. But remember, to run low diameter decomposition, you need non-negative weights. And so to find a graph with non-negative weights, since the most negative edge weight is -2, we can just add 2 to all the weights, and then we get a graph with non-negative weights, and you can run low diameter decomposition on that. So G+2 is only for low diameter decomposition. G+1 is like where most of the algorithm will be working. Okay, so that's kind of all of the preliminaries out of the way. We're now ready to actually talk about what the algorithm is. So I'm going to start by giving a slower algorithm that has runtime like m root m or m root n. And then later I'll talk about how to improve this to near linear time. So the algorithm I'm going to give, it's going to look like m root n. It's technically an m root n m root m algorithm, but I'm assuming every vertex is constant degree, which is why they kind of end up being the same. Okay, so remember, this is our goal. This is what we're trying to achieve, the scaling subroutine. And so the first thing we're going to do is we're going to go to G+2 and we're going to run low diameter decomposition with D equals something like root n. And now we have these three kinds of edges, right? We have the edges inside the green components, we have the black DAG edges, and we have the small number of red edges that goes backwards. And so as I said before, we're going to have three phases to fix each of these. So first, we're going to find a price function that fixes all the edges inside the green components, so that in G+1, all of those edges end up having non-negative weight. Now we apply that price function. So this is going to be the phases are cumulative. Like you apply phase 1, now you have a new graph where everything inside the green components is non-negative, but the black and the red edges can still be negative. So then in phase 2, you build upon this with yet a new price function that also fixes the black edges. And then after you apply that, only the red edges can be negative, and then you devise a third price function which fixes the red edges as well. So phase 1 is actually the hardest, and that's the one we're going to start with. So let's talk about phase 1. So what is the goal? You ran this low diameter decomposition, and now let's focus on one particular component. So you have a component with diameter at most root n, and you want to find a price function such that in G+1, all of the edges of that component become non-negative. Okay, so how do we do that? Well, let's start with a weak claim that I think will at least give some insight into which low diameter is helpful even when you have negative weights. So you have this component with low diameter. And I'm claiming that for any two vertices in that component, if you consider actually any path between them, that path cannot be too negative. The most negative it can be is -d. And the proof is straightforward, which is recall that we assumed that the graph doesn't have a negative weight cycle. So since this is a low diameter component, we know that for any x and y, there is a path from y to x of distance at most d. That's the whole point of low diameter component. Note that actually this path had distance at most d in the graph g plus 2. But that means that in G, the weights in G are even smaller than in G plus 2. So in G, it has an even shorter path from y to x. But definitely there's a path from y to x of length at most d. That's the whole point of low diameter component. But this means that any path from x to y the most negative it can be is negative d, because you're not allowed to have a negative weight cycle. If it was more negative than negative d, then you would have a negative weight cycle. Okay, so this red claim suggests that because your component has a low diameter, it sort of makes sure that things can't be too negative inside the component. And that's useful for us because we said negative edges are the hard part. But this isn't really strong enough, because even this guarantees that the path from x to y is not too negative, but it can still have many negative edges. It could be, for example, that the path from x to y is like -1, 1, -1, 1, -1, 1, -1, 1, and so on. So that overall path is not very negative, but it still contains many negative edges. But it turns out that once you switch perspective to G plus 1, you can ensure this stronger claim. So if in the original graph, your component has low diameter, then we can show that in G plus 1, you can say something much stronger, which is actually that every shortest path uses few edges. And here's the proof. So in particular, we want to say that if you use a dummy source, then the shortest path from the dummy source to any vertex y contains few edges. So this shortest path from the dummy source to y, right, it'll start by taking an edge of weight 0 to x, and then some path from x to y. And we want to show that that path from x to y contains few negative edges. So here's the proof. We're going to start by talking about G plus 0 and just kind of redo the proof we already did. So we know there's an orange path from y to x of length at most d, because this is a low diameter component. And that means that the distance from x to y is bigger than negative d, because otherwise you'd have a negative weight cycle. So the weight of this path in the original graph is bigger than negative d. Now, what happens when we switch to G plus 1? Well, in G plus 1, on the one hand, we know that the weight of the path has to be less than or equal to 0. And this is the one crucial point where we're using the fact that we're working with a dummy source, because the dummy source always has the option of just taking a 0 weight edge directly to y. So whatever path we use has to be non-positive. On the other hand, there's also this easy relationship between w plus 1 and w plus 0. Right? All w plus 1 is you added 1 to every edge weight. So the weight in G plus 1 is just whatever the weight was in G plus 0 plus the number of edges on the path. But the point is, in G plus 0, we know that the most negative you can be is negative d. In G plus 1, you're less than 0. So you added at most d, which means that there are most d edges in the path, because you add plus 1 for every edge on the path. So that's how we can conclude that the total number of edges on the path is less than or equal to t. And this is exactly what we wanted, because basically now what that means is that inside this component, you can just run Bellman-Ford to compute distances quickly. Because Bellman-Ford works well as long as you have few edges on the shortest path. And Bellman-Ford computes shortest distances inside the component. And as we said before, if you can compute shortest distances from a dummy source, that immediately gives you a price function where everything becomes non-negative. And so the running time is basically MD, because you only have to run D iterations of Bellman-Ford. So it's something like M over that. So to kind of summarize, the way we do phase 1 comes up with a price function to fix all the edges inside these components. And what the algorithm does is just for every SCC, SCC is strongly connected component. It creates a dummy source, and then it runs Bellman-Ford up to root n iterations. And that's enough by the lemma we just proved. And then it just sets the price function to be those distances. Okay, so we're now done with phase 1. So once we apply that, yes, go ahead. Yeah, feel free to ask questions.
Thanks. My question, so I guess we're computing these distances in G plus 1. I guess something I'm confused about, is it clear that we get the distances in the original graph from the distances in G plus 1?
Yeah, so to kind of that is not, we're just trying to compute a price function. So basically we compute this is a great question it's about how, so you compute the distances in G+1, and that gives you a price function for G+1. That gives you a price function for G+1 where every edge becomes non-negative. That's this here, because distances immediately give you a price function in any graph.
Right.
But that means that in G, all the weights are bigger than -1. Because if in G+1, all the weights are bigger than 0, in G, they're just exactly 1 smaller. So then they're bigger than -1. And that's all we wanted, right? Our goal is just to do scaling, where we started with weights bigger than -2, and now we have a price function where everybody is bigger than -1.
Okay. So we're computing distances in G+1, which gives us a price function for G+1, which tells us that in G, the weights are becoming less negative.
Exactly. So it doesn't directly compute distances in G. It just, makes weights in G less negative, and then you apply this scale down routine over and over again. But yeah, we're just focusing on this one instance where our weights start at -2, and we want to make them -1.
Okay, thanks.
Okay, so at the end of phase 1, all the edges inside the green components are now non-negative in G+1, but the black edges can still be negative and the red edges can still be negative. So the goal of phase 2 is to now fix the black edges. So ignore the red edges, we don't care about them. We just want now the black edges to become non-negative. So the way to do that is, let's think about the input to phase 2. By the time we're in phase 2, we already completed phase 1, which means all the edges inside the green components are non-negative. But we can still have these negative DAG edges between the components. And we want to somehow fix these. And this is by far the easiest step, because DAGs are really easy for this problem. All you do is set L to be an absolutely enormous number, like bigger than the absolute value of all your edge weights. And just set the first component to have, everybody in the first component has price -L, everyone in the next component has price -2L, -3L, and so on. So what happens when you look at any edge from U to V? What is its reduced weight? Well, you're adding phi of U and subtracting phi of V. But since V is in the later component, in the end, you're adding at least L. You're adding L or 2L or 3L, but you're adding at least L. And since L is enormous, you're basically adding at least L to all the edge weights, and so they all become non-negative. And note that an edge inside the component remains the same, because you're adding and subtracting the same thing. So the point is, the edges inside the green components were non-negative, and they remain non-negative. This new price function doesn't ruin them at all, but it does fix all the DAG edges. Okay, so that's the easiest phase. We fixed the DAG edges. So now we're at phase 3. So we now have a graph where the only negative edges remaining are the red edges. So we take that graph, and now we want to find a price function that fixes these red edges. And here's how to do that. So again, by the time we enter here, only the red edges are negative, because phase 1 and 2 fixed all the other edges. And remember that every edge is a red edge with small probability. That was just the promise of low diameter decomposition, that every edge is a red edge with small probability. And so intuitively, we're in a really good place, because we have an algorithm that works well as long as shortest paths have few negative edges. But that's exactly what's going to happen here, because the only negative edges are the red edges, and every edge has a low probability of being a red edge, which means that every shortest path in expectation only has a small number of red edges, and so only has a small number of negative edges, and so Bellman-Ford plus Dijkstra will run quickly. So in particular, we want to show the following. In words, this is just saying that if you look at every shortest path, it contains at most root n red edges. And the proof is really simple. I'm going to just give the proof sketch where I make the simplifying assumption that all the edge weights are like a constant. So in this case, for every edge, the probability that it's a red edge is 1 over d. That's just the promise of low diameter decomposition. So it ends up being something like 1 over root n. But basically, you have a path with n edges. Each path becomes a red separator edge with probability 1 over root n. And so clearly for every path, the expected number of separator edges is like at most root n. Now, for the actual proof, you have to deal with the fact that some weights can be bigger than a constant, but basically you can show that because you're looking at a shortest path from a dummy source, the total positive weight of the path is order n, and so you can apply the same argument. Okay, so that's, yeah, so the highlight here is just that basically in phase 3, you have few of these red edges, shortest paths contain few red edges, and so Bellman-Ford plus Dijkstra will be fast. So this is the algorithm. You create a dummy source, and now you just run Bellman-Ford plus Dijkstra in the whole graph from this dummy source, and it'll be efficient because shortest paths have few negative edges, and that gives you a price function. And then again, that price function, that gives you distances, and those distances immediately give you a price function for G+1. Okay, so this is the Emmerich algorithm. That's the whole algorithm. So the next step is to talk about how do we get this to be near linear time. So let's talk about why our current approach is stuck at Emmerich. It's basically because when we run low-diameter decomposition, we have to pick this parameter d for the diameter of the balls, of the components. So phase 1 wants a diameter to be small, right? Because if the diameter is small, then we basically prove this strong claim, which is that if in the original graph you have a component with small diameter, then in G+1, the shortest paths in that component will have at most d edges. And so the smaller d is the better for us. And so the runtime ends up being something like MD. But now phase 3 is the opposite, right? Because the way low diameter decomposition works is if you want really small components, you're going to have a lot of these red separator edges. Whereas if you allow large components, you only have a small number of red separator edges. And phase 3, basically how efficient it was depended on how many of the red separator edges you have on a path. And so basically you can show that the running time there ends up being something like you have n over d red edges on a path. And so the runtime is something like mn over d. And so to balance these, we picked d equals root n. So here's our strategy for making this faster. We're actually going to use a very large d. So we're going to have high diameter balls. So phase 3 is now really fast because if d is large, that means that an edge is a separator edge, a red edge with incredibly low probability. But phase 1 now seems hard because all we've guaranteed is that shortest paths have at most n over 2 edges. But note that this is actually progress. We started with a graph where every shortest path contains at most n edges, but now inside of each of our components, every shortest path contains at most n over 2 edges. So we basically have the number of edges on the shortest paths. And so if you just apply this recursively log n times until eventually all of your shortest paths have very few edges. So now let me state that more formally. Again, we're going to use recursion, and as we recurse, we're going to reduce the number of edges on the shortest path. And so we're going to need a new parameter to keep track of that. So we're going to use a scale down procedure as before, this main scaling subroutine, but I'm going to add one parameter delta. So the basic goal is the same. You start with a graph where all the edges are bigger than -2, and you want to find a price function such that all the edges become bigger than -1. But you also have the promise that in your input, all your shortest paths in G+1 have at most delta edges. So basically, when we first call this subroutine, we're going to call it with delta equals n, because clearly every path contains at most n edges. Now, the base case when delta equals a constant is also easy. If delta is a constant, that means every shortest path uses like a constant number of edges in G+1. So you can just run Bellman-Ford in G+1. It'll be efficient. That'll give you a price function for G+1. And as we said before, that gives you a price function for G that satisfies the scaling property. So the idea is we're going to start with delta equals n, and we're just going to keep recursively calling it with delta equals n over 2, and then delta equals n over 4, and then delta equals n over 8 until we get to this base case. So let's see how that actually works. So here's our algorithm now. So now we're going to, as I said, call it with d equals delta over 2. So if whatever delta was before, our new diameter is just like delta divided by 2. And so this guarantees that inside of all of our components, every shortest path contains at most d edges. That was a strong claim from before. So now d is delta over 2. So inside our components, all the shortest paths use at most delta over 2 edges. But that means that we're allowed to call scale down delta over 2. So that's the whole algorithm here. We're just kind of repeatedly decomposing to get smaller and smaller components. And you only end up with log n recursive calls in total. Okay, what about phase 3? So in phase 3, d is delta over 2. And so every cut edge is a cut edge with probability 1 over d. So intuitively, all your paths contain at most delta edges. And now every edge becomes a red separator edge with probability 1 over d. So in expectation, the number of red edges on a path is something like delta over d. But that's just a constant because we set d to be delta over 2. So every path only contains like a constant number of red edges, which means that by the time we get to phase 3, remember the only edges that can be negative are the red edges. So every path only contains like a constant number of negative edges. And so we have a good algorithm to handle that case. Okay, this is the whole algorithm. This basically completes the technical part of the talk. And definitely feel free to ask questions now if there are kind of technical questions. And otherwise, I'm just going to wrap up with like a few minutes of summary. Okay, well, I'm going to keep going with the summary and always feel free to ask questions about this. Okay, so basically we show a kind of a relatively simple combinatorial algorithm for this problem for negative weight shortest paths. And so to compare to sort of what came before, like previous combinatorial algorithms were all stuck at m root n. And then there's this other line of work using heavier machinery and dynamic algorithms that was able to solve this more general problem, min cost flow, in almost the same running time, but a bit slower. So I also want to talk about follow-up work that's been done since we published this result. One is that there's a result which really significantly, it's sort of using the same basic framework, but it significantly optimizes it and the algorithm has a different flow and it kind of just does everything better and really heavily reduces the number of log factors. So it's now something like log squared log W. And the second is that me and others are able to show that you can kind of, all of these ideas port nicely to the parallel distributed setting. So in effect, we can show that we can, in the parallel distributed setting, we can reduce the problem of shortest paths with negative weights to the problem of shortest paths with non-negative weights. So they're equally hard. Okay, let me then finish up with some open problems. So first, some open problems specifically about negative weight shortest paths. I think the biggest one is this. As I said, all of the algorithms for this problem are using scaling. If you have real weighted edges, the fastest thing known is still just Bellman-Ford and time mn. This is in contrast with non-negative weights, right? Dijkstra's does not need scaling. Dijkstra's works for real weighted edges. So we have this very fast algorithm for non-negative weights, but this slow algorithm for negative weights. So there's still a big gap for real weighted edges. I should add that as of like 2 weeks ago on arXiv, someone actually finally made progress on this. So Jeremy Feynman can do mn to the 0.9, which is really amazing, but there's still a long way to go. The second problem is to do this deterministically. So the min cost flow algorithm actually also, as of very recently, can be made deterministic. But if we want near linear time, nothing is known that is deterministic for this problem. So that remains open. Okay, and finally, just as a last slide, I want to talk about like this general open problem of can we, for other foundational graph problems, like design efficient, relatively simple algorithms that sort of tackle the problem directly and don't need to go through this elaborate machinery that we need to solve min cost flow. And I think the right starting point here would be bipartite matching. because it's like this very easy to define problem, and mroot_n is still the best known for these kind of simpler algorithms or for combinatorial algorithms. So I think making progress on that would be really interesting. Okay, thanks. That's the whole talk.
Well, thanks, Aaron, for the talk.
Thank you for inviting me.
Does anyone have any questions?
I have maybe one question. It seemed like in the SCC case, you were talking about how like a bad case in your analysis is when the paths are like length roughly order n in the number of nodes. I'm not sure if I'm correct.
So are you talking about phase one where we fix the edges inside the green parts?
Yeah.
Mm-hmm.
And it's like you want to argue that there's few edges on shortest paths. And I guess like I guess my thought is like coming from like having studied like distance preservers, we can we generally like it seems like a very unusual situation when paths are of length n, because then they're going to like the shortest paths are going to be overlapping a ton. And I was kind of wondering like, yeah, I don't know.
Right.
I guess it was surprising that's like a tough scenario in this.
Well, I think n was a bit of an extreme case. So somehow
Okay.
I think, yeah, I think it's likely that you can use hop sets to reduce the number of edges to like root n, or n to the 1/3 if you're feeling really ambitious. But you're not going to do better than that. At least not like with the general kind of. So the point is, in the original graph G, I think maybe paths of length n is unrealistic, but paths of length root n I think is totally realistic in the original graph G. And so that's why we kind of need to switch to G+1, which is penalizing the paths, and so making them have fewer edges is basically what's happening.
Okay, cool.
So that's why we have to go through scaling, which is a shame because that makes us not work for really weighted edges. But scaling allows us to work with G+1 instead of G, and so we're effectively penalizing the long paths, and that's the only way we know how to make them shorter.
Oh, I see. Cool. Oh, I have one more question. So like to go to the order m per bound, you do like this log n depth recursive like are you performing the low diameter decomposition each time, or
Yes. So basically why isn't it? Yeah. So basically you like perform low diameter decomposition, and then inside each component, you've now reduced the number of edges on the shortest paths just by half. And so you just like call the whole algorithm from the beginning on each component. So inside each component, you call low diameter decomposition again. Then in each, so I kind of think of this as merge sort, where like merge sort breaks the array in half, then breaks each of those in half, then breaks each of those in half. So here the breaking in half is being done by low diameter decomposition.
Okay.
And then at the bottom level, you have a bunch of tiny little components. And then the merging step is basically done by phase 2 and 3.
Okay.
That corresponds to then you're like building everything back up.
I see. Thanks. Okay, so you're generating more sep edges.
Yes,
time,
they're kind of, yeah, but it's like only like every edge only participates in like log n of these. Like they're only log n layers. So it's, yeah, you're only paying an extra log n. But this is where a lot of the inefficiency came from. That this is like how like this other, where we're basically like redoing a lot of recursion from scratch. We're like constantly throwing everything away. And so if you kind of look at things more, if you control the flow of the algorithm, you'll kind of realize that like what they're able to do is have a much cleaner, basically do much less recursion and much less recomputation.
I see. Thank you.
Yeah.
I have one question.
Yes.
Tell me what the round complexity of the distributed algorithm is for reducing from negative weight edges to graphs with non-negative weight edges.
Yeah, it's bad. It's bad because the positive weight edges problem is still hard for parallel algorithms and for distributed algorithms for like in congest. And so basically it's whatever the round complexity of solving the problem is for non-negative weights, we can match that for negative weights. But that existing round complexity for distributed algorithms, there's like a lower bound of root n plus d.
Yeah.
And the upper bound is a little bit worse than root n plus d. And so we sort of black box match that upper bound.
Okay.
Yeah, in parallel, then there's still, it's in theory possible that one can come up with a parallel algorithm that's fast for non-negative weight shortest paths, in which case our reduction will immediately apply that for negative weight shortest paths.
Okay. Yeah, I was just wondering what the cost of the reduction itself was, rather than the overall.
Right. Yeah, I think the cost is nothing. It's just solving the positive weight version times, a million log factors.
Okay.
Yeah.
Okay, great. Thanks.
Actually, no, sorry, I lied. Sorry. The cost to solve the positive weight times a subpolynomial factor. We're not able to do it with only logs. So it's like whatever the positive is times n to the little o of 1. And that's like an open problem that I don't know how to solve. Like for some reason in the distributed and parallel, we need this extra n to the little o of 1 factor. So it's not quite the perfect reduction I made it out to be, but it's almost there.
Okay, great. Thanks.
Mm-hmm.
So actually, the algorithm, I mean, it seems very implementable. Other than perhaps is the low diameter decomposition hard to implement, or?
It is not. I think so. I think Danyupan was having one of his undergrads implemented. So I do think yeah, it is implementable, and low diameter decomposition is also it's not hard to implement. I think one of the things that I don't like. I think we haven't done like a definitive implementation and comparison. So I can't really tell you exactly how well it works. I think this algorithm has a log to the 8th. So you'd probably have to be, a lot of the logs you can either optimize out, or you can just have a heuristic that, a lot of them come from probability stuff that you could probably just pretend it works better than it does in theory and it'll be fine. But you have to be a little clever. If you just implement it as is, log to the 8th will kill your algorithm. I don't know if they ever implemented the log squared version.
Cool. Are there any other questions? Okay. If not, I can take us offline.